Okay, so we're going to do a quick recap of the last two experiments, some takeaways. First experiment was pretty basic. Basically, you looked at the rheostat and you were varying the rheostat's resistance using a little slider. And you should have noticed that as you increase the rheostat opening, the current went down and vice versa. As you decrease the resistance on the rheostat, the current went up as we held the voltage constant. So that was kind of a lead into Ohm's law. And in your second experiment, you looked at trying to approximate resistances and voltages using Ohm's law and a variation of Ohm's law. So on the board here is what you should have done. Hopefully you got your report back and you make the appropriate corrections. So make sure you, if you didn't see it from your group member that submitted it, check with me or check with your group member. Most everybody on at least the second report should have seen the entire report. So in any case, so again, this is both Ohm's law, just flip-flopped. Might be used to seeing V is equal to IR, but I flip-flop so that you can kind of see it in the form of Y equals MX. So in this case, this would represent your slope, like you're used to seeing in your point slope formula. And on the Y-axis was the voltage, and the X-axis, which is also called the abscissa. Sometimes the author uses kind of big terminology for the X-axis. You should use current, and this is an amp. So you always want to note what your units are for the reader. I understand I'm the reader, but you also have other people in your group. You may have somebody pick up your report at a later point. So you always want to define your variables. And so from this, you should have gotten an approximation of what the resistance is. Now, everything's going to be a little bit, there's going to be a slight little tweak to it. We'll talk about that in just a minute, why that's going to occur. But I believe for one of your experiments, your resistance was roughly about 30 ohms, depending on what semester we're in. So you see this in the later semester, I may have changed it, but your resistance and your slope should be approximately roughly the same. So if you're off by a few ohms, we'll talk about why that is in just a second. And then over here, we looked at the relationship between current and 1 over the resistance. That's 1 over R sub S. Resistance of some source. And so the voltage of that source is what's to be captured here via the slope. So both of these are linear graphs, kind of basic. If you've forgotten some of your point slope equation, I encourage you to go back and remember point slope form of a line, Y equals MX plus B. And so now this is something that we didn't look at for this example, but it's kind of a lead in to the next experiment, which is the measurement of resistances in the Wheatstone bridge. And so just kind of want to look at, again, Ohm's law just in another format, just modified this by dividing both sides by I. I let R be the dependent variable along the y-axis measured in ohms, and 1 over I, that should be 1 over I, is the x-axis. So this is 1 over I. Oh, no, sorry. That's correct. So 1 over, so I is the is along the x-axis, but we're still graphing this equation, we're holding V fixed. So in a situation like this is a nonlinear graph, so you won't see a constant slope here. For those of you that taking calculus, you'll be able to figure out the slope depending on where you are on the graph by taking the derivative at a specific point, but that's not what we're trying to do here. My point here is to show you how large currents could give you small errors in resistance, but you may have noticed, and some of you guys did in the lab, that when you have a smaller current, there's a larger room for error, a bigger room for error. You can kind of see that from this graph. So that's going to kind of lead us into the Wheatstone bridge and why we look at the Wheatstone bridge. So let me pause for a second and come right back. Okay, so let's continue on with our look at this Wheatstone bridge. It's not as complicated as it looks. For the experiment, which you would have done or which you may have to do is look at two pairs of resistors that are in parallel with one another. And we're going to introduce a new component here, a new instrument called the galvanometer. A galvanometer is nothing more than an instrument to let us know where there's no current. In other words, when you look at the galvanometer, you'll see a little needle that'll toggle between 0 to one side or the other side of 0. And essentially, it's synonymous to our lab balances. Once you get one mass on one side and the other side to be the same mass, we have basically something that we're looking for essentially. And in this situation, when the needle reads 0, it's what we're looking for. We want the current to be equal to 0. So in this situation, we'll use G as the galvanometer, but if you're doing this via simulation, we're just simply going to use an ammeter, which will hopefully show to 0, which will show 0. So in our actual experiment, we'll use a wire instead of this looking like two resistors. We're going to use a wire, and we're going to position an alligator clip in this position. We're going to actually slide it along, you'll see in the next picture here, until we get the current passing through here 0. R sub D is the decade resistance box that you've already worked with. R sub X is just a resistor of a given resistance. So maybe 10 ohms, 20 ohms, 15 ohms. And then we have these 6 different points, A, B, C, and D, as well as E and F. So R sub 1 and R sub 2 would need to be determined if we were using the experiment in class. And the way you do that again is you would take your alligator clip and you would move it along this wire. And notice here, I've just changed the color of this resistor schematic to emulate that of a resistor. It's not actually a standard resistor that you're probably used to seeing, but it's more of changing the resistivity of the wire. So by moving the alligator clip, we do that. And that's done by this formula here. We're not going to get too deep into this formula other than showing by proof of a couple of equations how we got to our final answer. So if R sub 1 and R sub 2 need to be determined, the resistance of a certain portion of the wire, say this smaller portion R1, simply change this subscript to a 1 and replace it with a 1 over here, which I've done over here in this part of the equation. And likewise for 2, so the resistance of portion 2, or L2, comes by way of this equation. And again, Rho is just simply what's called a resistivity. Every different material has a various resistivity. Again, not to worry about that just yet. L is really the main mathematical component that you're going to be interested in. A is just the cross-sectional area of that wire, and we're going to assume it's uniform and they're going to be the same. Okay, so let's just say that we have this bridge now and it's balanced, which means, again, if the bridge is balanced, that means we have no current going through this wire here. We would set an ammeter or a galvanometer across that. Our alligator clip is here. We'll notice that the voltage drop between A and C is going to be equal to that of B and D. So from this point to this point, as well as from this point to this point, the voltage drop is are equal. And you notice I didn't put a specific voltage here. The voltage for this part of the theory is irrelevant. You can change the voltage to anything you want. Put a 9-volt battery or 10-volt, whatever you want your voltage source to be. So again, our bridge is balanced at this point. The resistance R1 and RD are in parallel to one another, as well as R2 and Rx. Again, we said that the voltage drop across this point is the same as the voltage drop across this resistor, as well the voltage drop across from C to E or across this resistor is the same as the voltage drop across resistor Rx. Okay, so once we have that in place, we're just basically going to use Ohm's law. So I just rewrote Ohm's law using this portion of the equation and rewrote it here. Likewise over here. So it's the current going through resistor D times the resistance of D as an example here. And then likewise for the other two resistors, R2 and Rx. And then we'll set these equations, we'll divide these equations. So I just rewrote this just as it is, just rewrote it here, just divided them out. Nice little tool we have that we can utilize. And notice here that, remember that the current going through resistor 1, which I call IAC, is the same as the current going through resistor 2. So those two cancel each other out. Likewise, the current going through resistor D, which is the decade box, and the resistor that's given are the same. We talked about this, how I came to this conclusion that the resistance of this part of the wire, which I call R1, is now emulated using this formula, rho L1 divided by the cross-sectional area, and likewise for R2. So the rows are going to cancel out, same material, same resistivity, cross-sectional area cancels out, and we come down to this conclusion. So if we were doing this in class, basically what we should see is that the ratio of the two lengths would be equal to the ratio of the two resistors. So let's just say that you set the decade box to, I'll just say 100 ohms, and you had a resistor here, a given resistor, let's just say of 10 ohms. You should see a ratio of 10 to 1 in this little area here. We're gonna have a meter stick, so that would probably mean that you would have, let's see, if the length of the meter stick where the clip was would be, let's just say, this would have to be roughly, this one 10, the meter stick we're at 10, we could figure out what X would be. We'll do a little bit of cross multiplication. Let's see, that would be 1,000. And over here, we would get 10X. So X would be roughly at 100. Now that probably wouldn't work per se, because we're going to be on the wire is only a meter long, but we're going to see a ratio of 10 to 1 between these 2 points. So this would probably be some, I just used clean numbers here. So this would probably be some function so that it's kind of scaled down to being on a meter stick. So you would basically see whatever number this landed at be 10 times less than the length over here. Okay, so it's just a matter of playing ratios here. Okay, so that would be how you would use the experiment, how you would complete the experiment using the alligator clip, the wire, and the Wheatstone bridge, the mechanism that we have. Now, for theoretical purposes, what we're going to do is we're going to probably just look at it in terms of ratios. If you've looked at similar triangles, pretty much the same. So there's a lot of theory here, but if you break it down, it just comes down to just simply ratios. So let me just zoom in here real quick on this quick example. Okay, so if I have 2 resistors of known resistances, 10 ohms and 30 ohms, and I have another resistor over here of 3 ohms, and we want to balance the bridge, we'll just simply set up a ratio 10 to 30 is equal to X over 3. And you can see that this is pretty easy. We should see that this balances out to be 100 ohms. Okay, so